This is topic 1.3, energy and equilibrium. So last time we talked about how to model systems and how to follow in an open system the flow of energy and mass. This time we're going to talk about how we can have an equilibrium. And basically where we're heading on this, the big idea is a system which is sustainable. In other words, you can take things out of the system as long as you put things in there and there's a balance. In order to do this, we need to understand the laws of thermodynamics. So let's talk about the first law, the principle of conservation of energy. Energy can neither be created nor destroyed, but it is only transferred. So what we can see here is that in a very, very simple system, the energy that comes in through photosynthesis creates food. Chemical energy is then transferred over to this kid who's eating it. The kid then has kinetic energy, the energy to play on a bicycle. And we would assume that this is a stable situation, right? That as long as the sun keeps pushing energy this way, the output is still okay for the kid. So we saw that solar energy is transferred into chemical energy and then kinetic energy. So most energy is starting from the sun and then processed through. Most solar energy, though, is not absorbed. It's probably reflected or it's shielded from us. Less than 1% of the sun's energy is actually being used. And there's always waste. So every time you move and transfer something, there's a certain loss. Nothing is 100% efficient. And the most common place that energy is lost is pretty much through heat. And we'll see that even as we eat food. We don't absorb all the energy. A lot of it is lost as heat. When we transfer mechanical energy into machinery, a lot of it's lost as heat. But the first law says, in a perfect world, there should be conservation. So you have to account for energy being lost. So if I only get 10% energy from something, I have to assume that 90% was lost. That's the law of conservation of energy, first law of thermodynamics. The second law is a little more interesting, a little more subtle than the first one. The second law is the law of entropy or disorder. Basically, what it is saying is that as energy moves through a system, things get more disorganized. Think about it like this. Let us suppose that I have a beaker and I put some perfume in the beaker and I put it on my table in the front of the room. What happens is that as that starts to enter the air and diffuses through the room, eventually the students in the back will begin to smell it. It has left the beaker and it is diffusing out onto a greater area. It's becoming more disorganized. It started off just as a small few drops in a beaker, and now it's all covering through the room. That's the law of entropy. The natural order of things is that they become more disorganized as we go along. What does this mean? Well, it means that as solar energy went into plants, and then chemical energy, and then to the kinetic or mechanical energy, we lost energy because it became more disorganized. So let's take a look at how this would work in living things. So producers, that is plants that use solar energy here, then are eaten by primary consumers, a cow, shall we say. Then secondary consumers, herbivores like ourselves, might eat it, or tertiary consumers, carnivores. And we go up a pyramid. Now what happens as we go transfer from one level to another? We're losing energy. We're losing energy. Now here's the interesting thing though. As we're losing energy, things become more disorganized, shouldn't they? Well, they should become more disorganized, but sometimes they don't. And the only way they could not become more disorganized is you have to put in a greater amount of energy into the system. Okay? So let me say this again. basic idea as we transfer energy is 90% is lost. Now, we often refer to this as the 10% rule. In other words, only 10% of energy is being moved from level to level. Things should become more disorganized. However, sometimes molecules become actually bigger and more complex. Now, how is that possible? If the law of entropy says things should become more disorganized, and the only way that could happen in a closed system is that actually you're putting in more and more energy into the system to create more complex molecules. So how do things eventually reach a steady state? Well, you have fluctuations around a set point, yes, but in an open system, you eventually just reach a mean level. For example, a fallen canopy tree in a rainforest. It falls, and that's the end of it. This is very common in an open system. A static equilibrium means there's no fluctuations whatsoever. For example, a chair. It is where it is. It's not moving. Nothing changes. Now, these two states that we talked about so far are not all that interesting, and we're not going to talk about them all that much in the course. A stable equilibrium is something we'll talk about a lot. We have a set point. It goes above the set point. Something happens to bring it down below, and then something happens to drive it back up again, and it keeps compensating to get it back to the set point. This is what we call negative feedback. And a really easy example of that is, of course, your thermostat in your house. As the set temperature changes because it gets hot, the air conditioning comes on. As the set temperature changes because it gets colder, the heater comes on. It always tries to get back to the nice temperature you want the house to be in. And this is an unstable equilibrium. This is what we call positive feedback. A disturbance happens, and instead of it going back to where it is, it gets further away from where you started. A lot of examples that we'll talk about later on this year in global warming have to do with positive feedback. What causes these changes to happen? You pass over a tipping point. This is a critical threshold that then causes that dramatic event to take place. So it's very interesting in ecological science that oftentimes you can have stimuli and you still don't see a change in the output. There has to be a certain tipping point for it to happen. For example, we saw that you can increase carbon dioxide levels quite a bit and nothing really happens to the temperature of the planet. It isn't like a little bit of carbon dioxide causes a little bit of temperature. There had to be a tipping point, and we found out the tipping point was 450 parts per million. At that point, temperature does start to increase, and that's when we see glaciers start to melt. Fortunately, the planet and many systems have the ability to fight back, and that is called resilience. They have a tendency to avoid these tipping points. So, for example, grasslands. After a fire, a great disturbance happens. You would think things get wiped out. But it turns out that there is resilience, that in the soil, down in the ground below where the fire hit, there still are seeds and sprouts and nutrients to regenerate the grassland. We've seen this, for example, in Mount St. Helens, which blew its top in 1980, decimated a whole area. Yet if you go back up there, there's resilience. A lot of it has come back. Whereas we will discover we can destroy the ability of systems to have resilience. For example, in wheat farms which have monoculture, if they get burnt down, that land does not come back. And that concludes this topic.